All right, so we're going to look at exponential growth and decay models along with what we were doing with our differential equations. So this starts by saying, in many applications, the rate of change of a variable y is proportional to the value of y. Okay, thank you. If y is a function of time t, the proportion can be written as shown. So basically, we need to know how to write this if we see these words. So the rate of change, that's a dy dx, dy dt, whatever it is, depending on what the variables are. In this case, it says we're using t and not x. So the rate of change, that's our derivative. It's proportional to the value of y. And k would be whatever our proportion is. But we got to be able to set something up like that from those words using the appropriate variables for whatever it is that we have. So let's solve this differential equation to find the general, we're going to look for the general solution. So I'm just going to rewrite this right here. dy dt equals k times y. Okay, so I want you to do what we've been doing. Separate the variables, integrate, find the general solution. Okay, basically the exact same steps that we've been doing for a few days. Go for it. Yeah, go ahead and do the whole thing, yeah. And then I'll work it out too. We'll just see where we get. K is a constant. And the variable is t. Okay. I was trying to figure out what you had those with those. Yeah. Okay, but if I'm going to integrate this, I'm okay with that. Or integrate this, we're going to drop the dt, and you're going to have a plus c. And then you got to solve for y. Okay, good. So now integrate both sides. Yes, you're on the right track there. What? You're on the right track. No, you are. Well, I mean, you need to integrate. So once you integrate, then what be 0? Right, but like on right here, you might not, it's fine to write this step. Totally fine. I would probably leave it at this step because then I know how to integrate that. And it's not the power rule. How do you integrate 1 over y? Natural log. That's an L, but yes. I know. It looks like an I. It's an L. Okay, very good. Okay, here's where we integrate, right? 1 over y integrates the natural log of y. Then solve for y, if you haven't done that yet. Do what? It is cold here today. What happened to your T? What happened to your T? Okay, when you integrate it, you don't even have it here. Oh, never mind. It is right there. But then it just... Because well, you can't just copy what Daniel does. This is why you can't. Okay, so if so I get here, right? Since I need to get rid of my natural log, e becomes the base, these become the exponents. So then on the left-hand side, e to the natural log of the absolute value of y is just going to become y, right? Over here, because I am adding these in the exponents, I can make that into e to the kt times e to the c. And you could skip that step if you wanted to, because e to the c is still just some constant, right? So that in itself becomes c. And so I would get y equals c times e to the kt. Okay. Now, this is good. Will happen every single time. You have to set up something like this when you integrate it, because if this is going to be a consistent thing that shows up, you know that if you see these words, the rate of change of a variable is proportional to the value of the y or whatever it is, and you can set this up, it's going to end up looking like this. Okay, so we don't have to go through those steps every single time. That's basically what this is saying right here. If y is a differentiable function such that this is true, dy dt equals k times y, for some constant k, then we get this, which is what we just came up with, all right? Which means that c is the initial value of y. So let's think about that. If t equals 0, so if I substitute 0 in here for t, that makes my exponent 0, which makes e to 0 1, so then you just get y equals c. Okay, does that make sense? So when t equals 0, we've got y, so that gives me y equals c times e to the k times 0 power. That's where that 1 comes from. And what you get then is y sub 0 equals c. That's your initial y, your y sub 0 there. Then k is the proportionality constant. It's a constant. That's mainly what you need to know. But this is why we're saying dy dt, the rate is proportional to y. That's your proportionality constant, whatever makes it proportional. Exponential growth occurs when k is greater than 0. Decay when k is less than 0. Okay. Everybody okay with that? Everybody okay with that? All right, so let's look at this. I know. So funny. All right, the rate of change of y is proportional to y, and we're using t. So that means that dy dt is equal to k times y. That's one thing that we know, right? If that is true, then I know that y is equal to c times e to the kt. These are two things that we know just from this first sentence right here. Okay. When t equals 0, y equals 2. So that means that y sub 0 is equal to 2, and that is what your c value is. Does that make sense? That is your initial y value. When t equals 0, that's your initial one. That is c every time. Everybody okay with that? Okay. So this part right here is where that is coming from. That means that we can rewrite this as y equals, instead of c, I know that's 2 times e to the kt. So I want to find the value of y when t equals 3, but I had to figure out what c was. I also have to figure out what k is before I can figure out what my answer actually is. You with me on that? Like, I got to get my whole equation. So then this tells me right here that when t equals 2, y equals 4. So that means that I can substitute this in here and here. I got 2 more things I can substitute in. Doing 0 and 2 again is not going to do me any good. But if y is 4, that has to be equal to 2 times e to the k, which I don't know, times 2 power. Everybody good with that? Now I got to solve for k. So I'm going to start by dividing both sides by that 2. So this gives me 2 equals e to the 2k power. Yes? So then I can take the natural log of both sides to get that out of the exponent. So this is going to give me the natural log of 2 equals the natural log of e to the 2k power. Natural log of 2 is natural log of 2. That's not a number we know. What is the natural log of e to the 2k power? 2k. Very good. So natural log of 2 is equal to 2k, because the 2k comes out front, right? We're just skipping those steps. It can come out front, and the natural log of e is 1. So then that means that k is equal to, we can either do natural log of 2 over 2, or we can do 1/2 natural log of 2. It's the same thing either way, but those 2's don't get to cancel each other out. Everybody with me so far? All right, so now we can write our entire equation. Y is equal to e, no, it's not, 2 times e. K is 1/2 times the natural log of 2 times t. Yes? Now can we find the value of y when t equals 3? What do? Substitute it in. So that means that y is equal to 2 times e to the 1/2 times the natural log of 2 times 3 power. Do we want to go any farther? No, we do not. Okay. That is our y value. Everybody good? Okay. This, although it looks not pretty, look at what we were just substituting numbers in and doing a little bit of algebra, right? It's not that bad. Any questions about where anything came from? Jaden, you look like you got a question. Okay. All right. Anybody else? Okay, good deal. All right, then flip this over. The rate of change of v is proportional to v. So that means I'm not using y this time, I'm using v. My x variable really is t here, so I can say that dv dt is equal to k times v. Okay? Everybody okay with that? It's the same thing, we have v instead of y. So that means that we know that v is equal to c times e to the kt power. All right, so they tell us, so that I got all that just from this first sentence. Then they tell us when t equals 0, v equals 20,000. What does that give us? C. That tells us that C is equal to 20,000 because that is our initial y value, or our initial v value in this case. So that means now we have v equals 20,000 times e to the kt. Then they give me, when t equals 4, v equals 12,500, and I want to know what the value of v is when t equals 6. So what am I going to do with the information I underlined in green? Plug it in. Plug it in and solve for k. Go ahead and do that. think you do too. Okay, you cannot do this until you move this. Does that make sense? Okay, good. You're not finished. You got K. That's most of it. Now you got to rewrite your equation with K in it and actually substitute it. Okay, let's talk about process a little bit. Right here at this step, I cannot take the log of both sides right here. I can't do that until the exponential is isolated, which means that 20,000 has got to go. So I divide. Now, can I reduce what's on the left-hand side? Yes. Do I have to? If I don't have to, I probably shouldn't. Now, I saw something that you could kind of do a middle of the way, and Caden had it, but then I'm guessing that Daniel didn't, and so he changed it. Well, I didn't get because I didn't get any farther. But I could just knock off 2 zeros on both, and then it's less to write. Like that, I can make it 125 over 200. Would you agree with that? But I don't have to do that. I can leave it exactly like that. Unless it's a multiple choice question, which this one isn't, but there's no need for me to do that, so don't do it just because you don't have to. I wouldn't try and risk anything. At this point, we can take the natural log of both things. Now, something I think I saw in somebody's paper, when we do this right here, we put the e's down here because this is the base and these are the exponents. When we're taking the natural log doesn't go down here. Because we're taking the natural log of both sides, then this is going to give me, if I'm going to show it right here, I'd put natural log here and natural log here type of thing. Which is really not above it, I just can't fit it in front of it. Either way. So then here I get the natural log, and I'll just go ahead and leave it, bless you, of 12,500 here, and then this is equal to what? 4K? Okay. That means that K is equal to 1/4 times the natural log of 12,500 over 20,000. Okay. Now, if there were a lot more zeros, I might really make sure I knock off the zeros just because I don't want to not write the correct amount of zeros. That could be a problem. All right, so then we are now looking for what is the value of v when t equals 6? Well, I need to actually write my entire equation now. Oh, that's not a y. It is a v. Sorry. v is equal to 20,000. I don't get to leave off any of these zeros. Times e to the 1/4 times the natural log of 12,500 over 20,000 times t. What is it? It is 5/8. 5 over 8. If you did reduce it and you got 5/8, totally fine. You didn't need to, you were okay. If you reduced it and didn't get 5/8, that's bad, bad, real bad. Okay, but it is 5/8. All right, so then V is equal to 20,000 times e to the 1/4 times the natural log, all this stuff. Which, yeah, 5/8 would definitely be easier to write at this point, but what if we don't reduce it correctly, right? All right, what questions we got? We good? Awesome. All right. Example 3. Population Y grows according to this equation where K is the constant and T is measured in years. If the population doubles every 10 years, then the value of K is blank. Okay? So I want you to, I'm going to give you a few minutes. You can talk amongst yourselves there. Think about what you've been given. Write down what you can. See if you can find K. And we're not going to, this is a multiple choice question. This would be a calculator question. We're not going to worry about putting it in the calculator because we'd have to do part of this by hand anyway. So just find K. You're not going to be able to match it up unless you're some sort of savant that can do natural logs in your head. But very confused. Okay, but you don't have to do all of this. If we have this right here, we know it gives us that. So you're doing too much. So it automatically gives me that, what I have up here. Okay? Yeah, because this, I mean, technically this is right, but you're also trying to, in this case, we'd really be solving for y. Like, there's too many variables in there. Okay, let's think about what we know. When t equals 0, what does y equal? What is it? If t equals 0, what does y equal? 2, not 2. When t equals 0, what? If I substitute 0 in there, what am I going to get? E to the 0, which is 1. So what does y equal? C. Your initial y value is always C. When t equals 0, y equals C. Yes? Okay. So then, and I know we've actually been getting C. That's the best I can do right now. But it says that the population doubles every 10 years. So if t equals 10, what does y equal? 2 times C. Right? Do we agree with that? Okay. So that means that if I want to look for, I have the y value, I have an x value, and I know what's happening up here, so I can substitute this stuff in to here. If my y value is 2 times c, that's equal to c times e to the k times 10 power. You agree with that? Okay. So now, can I divide both sides by c? Yes. I can divide both sides by c, and when I do that, I'm going to get 2 equals e to the k times 10 power, or 10k. Let's do 10k. How do I get that k out of the exponent? Okay, take the natural log of both sides, so that means that the natural log of 2 is equal to what? 10k. So then k equals natural log of 2 divided by 10. We didn't even have to find out exactly what c was. Okay? But this is an important part. When t equals 0, y equals c. Period. End of story. If we have this sort of equation going on. Right? We good so far? I'll take that as a yes. Okay. Got the little light bulb one off here. Oh, so the answer is, you'd have to put this in the calculator. The answer is A. I mean, I don't expect you to know that from that, but we need to be able to find that. Okay. The population of bacteria in a culture is given by the differential function where y of t is measured in thousands, t is measured in days. Okay, so y of t is measured in thousands. We probably need to pay attention to that. T is measured in days. The population of a bacteria increases according to this equation. Okay, so this time it didn't say that the rate of change of the population is proportional, but that's what this means. So the rate of change of the bacteria is proportional to the y value there, where k is the constant, time t equals 0, the population is 45,000 bacteria. So here's what we know. We know that dy dx is equal to k times y. When this is true, when we have this proportional relationship, then y is equal to c times e to the kt power. Yes? What is c? Y. Y is c when? When t equals 0. So at t equals 0, y equals 45,000. So what is c? 45, yeah. So y is equal to 45 times e to the kt power. But it's in thousands. So it's measured in thousands. So when it says measured in thousands, that's why you put 45. You don't put 45,000. But there's a lot of things that we've had where it's measured in thousands. Like your y values might be 1, 2, 3, 4, 5, but it means millions of people or whatever. So, yes. Yeah. So we're not putting 45,000, we're putting 45 because it's measured in thousands. Y is thousands of bacteria, not just bacteria. Your units are thousands of bacteria. All right, so we're here. We have the increasing rate. Is it increasing? So right then, at this point, okay, so when this happens, it is increasing at a rate of 15,000 per day. So what equals 15,000 per day? No. T is the number of days, right? The thousands of bacteria is your y. This is the rate, 15,000 per day. This is a rate, right? So what on here represents a rate? dy dx, okay? So dy dx equals 15, right? Okay? Yes? No? Okay. And then 15, that's my dy dx. Well, here, to substitute it into this. Dy dx is 15. That's equal to k times, what is the y value when this is the rate? 45. Okay? Because remember, this isn't a rate for the entire thing because the rate of change is changing, yes? Because this is not a line. So when t equals 0 and this is the population, the rate at that moment is 15,000. This represents a rate. So I took 15, dy dx equals 15. I substituted it in right there. That's equal to k times y. And when this is the rate, my y value is 45. That means that k is equal to 15 over 45, which is 1/3, but we could leave it like that also, right? You just leave it. Just leave it so we don't do anything stupid. And then it says to write an expression for y of t. So y of t is equal to 45 times e to the 15 over 45 times t power. What questions do you have? Remember, math is a language. We are interpreting from one to the other. When you see the word rate and your units are in some sort of rate, that is your derivative. Don't try and be substituting it anywhere just because you think it should be like the one right before it. Okay? We okay on all that? All right.